All right, so this video, of course, we're going to be working some example problems for torque. Try to get as many kind of looks into the different ways of doing torque problems, but at the end of the day, they all have torque is R cross F, where R is the distance from the point of rotation to where the force is applied. F is what force is being applied, and this is called a cross product, a very fancy version of multiplying for vectors, which at the end of the day, for our purposes, basically means take the perpendicular component of the force and multiply by the distance. So if the distance from the point of rotation to the force is in the x direction, then you need the y component of the force. If vice versa, the distance from the point of rotation to the force is in the y direction, then you need the x component of the force. Okay? So it's always perpendicular. It's the opposite of work. Work was parallel. How much is in the same direction? For torque, the cross product, we're talking about how much is perpendicular, the opposite direction. All right. Also note any torque which makes my system want to rotate counterclockwise will be called positive. Okay, that's just standard. It doesn't have to be. It's the same as calling upwards positive and downwards negative. If you want to do the opposite, fine. But you better let the person who's looking at your work know that you're not doing the standard, you're doing the opposite. Because they're going to assume you're doing it the standard way. So when they see a negative, they need to understand what you mean by negative. All right, so let's start off with an example. This example is similar to one we did in the last lecture. We have a pole. Let the length of the pole be L. At the end of the pole will be hung a sign whose mass is 10 kilograms. This time, however, there will be a little wire which is tethering this pole to the wall, kind of holding it up, making sure that the pole doesn't collapse. Let's say that this tether makes an angle of 30 degrees with respect to the pole. And also, let it be joined to the pole about 3/4 of the way to the end. Okay? So the wire isn't hooked to the end of the pole, but at the 3/4 mark. Finally, the pole itself will have a mass. Let the mass of the pole be, let's say, 20 kilograms. And of course, we're going to let the mass of the pole, well, I'll discuss that. This is a situation. You have a pole sticking out of the wall. It's anchored into the wall. The pole itself has a length of L, and its mass is 20 kilograms. There's a sign hung at the end of the pole whose mass is 10 kilograms, and the pole is tethered to the to the wall at the 3/4 mark. And the way it's arranged, this rope, this wire, makes an angle of 30 degrees. The question is, what is the tension in the wire? Specifically, if this pole does not collapse, if it's balanced, if it's in equilibrium, what's the tension in the wire? Because obviously, if the wire is trying to hold up this pole, there must be some tension. And in fact, the tension is a force which runs through the wire called T. I want to know, what's this T? All right, so fairly complicated sounding question. Let's try to figure out how we can go about solving it. first thing I know is I'm assuming the pole will be in rotational equilibrium. And what that means is the sum of all the torques acting on a pole better be equal to 0. Next, I need to know how many torques are on this pole. So how many forces are there? Well, I've got a force due to the sine, I've got a force due to the weight of the pole, and I've got a force due to the tension. So there's going to be 3 torques. Okay. Torque 1. Let's say torque 1 is the sine, torque 2 is the mass of the pole, and torque 3 is the tension. So for torque 1, what is the torque? Well, first of all, what's the length? What's the distance from the point of rotation to where this force is being applied? Well, the point of rotation, of course, is the wall where the pole is anchored. And a force is the sine. So the distance is the full length of the pole, L. Which direction is this distance? Is it an x distance? Is it a y distance? What is it? Well, if I want to move from the point of rotation to where the force is being applied, I need to move in the x direction. So this is an x directional distance. That implies the force I need is a y force. So I need to know how much of my force is in the y direction. Well, the force, of course, is the weight of this sine pulling down. So it's already in the y direction because it's pulling down. And it's mg, so it's 10 times 9.8. And then lastly, is this a positive torque or is it a negative torque? Positive makes my pole want to go counterclockwise. Negative makes my pole want to go clockwise. That sine, if I'm pulling down where the sine is, the pole wants to go clockwise because of it. So this is going to be a negative. So we have negative 98 times L as torque 1. Now let's look at torque 2. Torque 2 is R cross F for him. So I say, okay, what's the distance? Well, here's the thing. This is just a rule. If you're given a nice, balanced, even object, like a pole or a meter stick or a seesaw, for our purposes, we're going to assume they're all nice and balanced. Then when you're given the weight, when you're given the mass of that object, you could just pretend like the full mass of that object is placed at its center. Now in real life, this isn't necessarily true. Maybe one side is thicker than the other, and so the mass is shifted over. But for our types of problems, we're doing more simplified problems. Assume this pole is even. So we can assume the weight of the pole itself can be thought of as being at the center of the pole. So, with that said, the distance from the point of rotation to the weight of the pole is to the center, which is half the length of the pole. So it's L over 2. Half the length. Again, this is an x distance, so I need a y force. What's the force here? It's the weight of the pole itself pulling down, so it's y direction. And it's mg, 20 times 9.8. Is he positive or negative? Well, just like before, if it's anchored on the left and I'm pulling down on the right, the pole wants to go clockwise, so he's negative. So what do we get from this? Negative 98 times L. Happens to be the same number, but that's a coincidence. All right, last one, torque 3. Torque 3 is a little more complicated. First, what's the distance? Well, this Wire is hooked in at the 3/4 mark, so the distance is 3/4 of L. Whatever L is, I don't know. But that's the distance. What's the force? Well, the distance is an x distance, so I only need a y force. Is the tension in my wire a y tension? No. This tension is pointing at the 30-degree angle. So what do I want to do? I want to make a little triangle and only get the y component of the tension. So if the tension is T, and this little triangle makes an angle of 30 degrees, the y component is the side opposite to the angle, which means sine. So it's T sine 30. That's the force. The force is tension, called T, but I only want to know how much of that T is in the y direction. So I'll make my triangle just like I've been the whole semester, and I get the y component of the force, which is T times sine theta, or sine 30. Finally, is this positive or negative? Well, if I pull up on the wire as the tension's pulling up, trying to make sure it doesn't fall, that force is trying to pull upwards, making my pole want to go counterclockwise, so he's positive. So what do we get here? Here we get 3/8 times L times T. Now notice I don't multiply by 9.8 here. In the other two I did. Why don't I multiply by 9.8? Well, the reason is because in the other two, torque 1 and torque 2, I was given the mass. But what I need is the force, and force is mg. So I take the mass times g to give me the force. For torque 3, however, the tension is a force. So I just take tension. Whatever the tension is, that's the force. There's no need for 9.8 there. So there we go. I've got my 3 torques. First torque is for the sine. Second torque is for the mass of the pole itself. And the third torque is because of the tension in the wire. Now all I have to do is add them all up. Minus 98 times L, minus 98 times L, plus 3/8 L times T equals 0. Now, notice there's an L on every term here. So they will all cancel out. L goes away, L goes away, L goes away. This is only true if every term had an L. If one of these things doesn't have an L in it, you can't cancel it. But here they all do, so I can cancel it. And that's why I didn't tell you the length of the pole. I could have told you it's 3 meters, then everywhere you have an L, you just put a 3 there. But it turns out, no matter what the length of the pole is, we could do it without knowing it. So don't let that confuse you. Even though we didn't know the length of the pole, it turns out it canceled out here. I could have given you the length, you could have used it, but whatever. All right, so what's left? I want to solve for T. So we have minus 98 plus 3/8 times T equals 0. So 3/8 times T equals 196. Solve for T, and I get 522.67. So that's how much tension would be in this wire. Now, if you're an engineer, you would want to do this because if you want to design this system, then you need to know how thick the wire should be so that it can handle this kind of a load. Because if the wire is too thin, maybe it can't support 522 newtons. So, when going to design systems, you need to be able to do these types of calculations because it's up to you to say, oh, you need this gauge of wire or this material to handle the stress or the load or whatever the case may be. But for our purposes, all we needed to do was calculate the tension, and we did it. Sum of the torques is equal to 0. We had 3 different forces, so we have 3 different torques. Plug in all the numbers, solve for your unknown. Now I did it where some of the work I did over here on the right, that's just so that you could see specifically what I'm doing. If I were calculating this myself, I would have done it all under the equation. I wouldn't have torque 1 separate from torque 2. That's just so that you could visually see what I'm doing a little easier. All right, let's try another example. Let's try a meter stick is balanced, but this time we place the fulcrum at the 40 centimeter mark. I place a mass of 3 kilograms at the 20, and I want to know if I have a little mass. Here it is here, and that mass is 1 kilogram. I want to know where I should place it if the mass of the meter stick is, let's say, 0.5 kilograms. Okay, so that's the question. You have a meter stick. You put the fulcrum at the 40 centimeter mark, so it's not at the center. You know how heavy the meter stick is. You place one mass at the 20 centimeter mark. That mass is 3 kilograms. And you have sitting on your desk another mass whose mass is 1 kilogram. And you want to know, where should I place it on this meter stick to balance everything? All right. So how are we going to go about doing this? The first thing is to note, if I don't know where to put this mass, then let's just assume I put it somewhere. First of all, I can assume I'm going to put it on the right. Because if I've got a mass on the left, to balance it, I have to have a mass on the right. So let's say I put it right here. Okay? Where is it? I don't know. But I'm going to put it there, and then I'm going to figure out where that is. The next thing is to note, where it is depends on your definition. Okay? I'm going to call the location X, but there's 2 ways of calling it X. I can either say the number on the meter stick is the X centimeter mark, so like the 80 centimeter mark or the 78 centimeter mark or something. And that's what X is. Or I could say the distance from the fulcrum to the mass, that distance is called X. Okay? That's also true. So maybe it's 20 centimeters away from the fulcrum. For our purposes, that's what I'm going to do. Okay? And I'll tell you, if you do it the other way, how things change. But for now, let's say this is how I do it. I'm going to place it at a certain point, and what I know is that it's X centimeters away from the fulcrum. All right, so let's start calculating. Sum of the torques is equal to 0 if this is balanced. What are all of our torques? Well, of course, we've got the 3 kilogram guy. So his distance is from 20 to 40. So it's a total of 20 centimeters. Note this 20 is not where he is, but it's from where he is to the fulcrum. So from 20 to 40 is 20 centimeters. Okay, you're not putting the centimeter number, you're putting how far away you are from the fulcrum. And in this case, it happens to be 20. Next, we need the force, which is 3 times 9.8 mg. And then, is this counterclockwise or clockwise? Well, if I pull down on the 20 centimeter mark, that makes my seesaw want to go counterclockwise, which is positive. All right, next, what do I have? I've got my little 1 kilogram guy over here. Where is he? Or what's the distance? The distance is x. From 40 to wherever he is x centimeters away. So it's a distance of x. What's the force? Well, it's 1 times 9.8. Is he positive or is he negative? Well, if the fulcrum is there and I pull down at the 1, pull down here, that makes my seesaw want to go clockwise, so he's negative. All right, so is this it? Set this equal to 0, solve for x? No. And it's no because I want you to think about this. Let's say I pulled the two masses off. So I got rid of the 3 and I got rid of the 1 and I just have the meter stick sitting there on the fulcrum. What's going to happen? Well, obviously what's going to happen is the fulcrum's going to fall down clockwise. And the reason is because the fulcrum is not at the center. It's not balanced. It's off center. So there's more meter stick on the right than there is on the left. So the right side's heavier. Well, my equation I have written doesn't take that into account. That's messing with things. So I need to worry about that. How do I worry about it? Thankfully, it's really easy. I'm told that the meter stick has a mass of 0.5 kilograms. And I already said in the last example, if you have an object and it's even and all of that, you could just assume all of the mass is at the center. So let's do that. Take this 0.5 kilograms, let's place it at the center. And just pretend it's another mass. So there's the 0.5 and he goes at the 50 centimeter mark, the center. So now we have another torque. What's the distance? It's from 40 to 50, which is 10. What's the force? M, 0.5 times G, 9.8. Is he positive or negative? He's negative because it makes the seesaw want to go clockwise. And now we have all the torques in our problem. We've got the 3, we've got the 1 we place somewhere, and then because the seesaw is not balanced at the center, we have the mass of the seesaw itself. Now we can set it equal to 0 and go. All right, so is there anything we could cancel? Well, every term has 9.8. If every term has 9.8, you could cancel them out. So there they go. What's left? We've got 60 minus 1 times x minus half of 10, which is 5, equals 0. So x is 60 minus 5, which is 55 centimeters. Now, do I box this answer? That's the question. Well, let's think. What does x mean again? Do you remember what we defined x to be? X was defined to be the distance from the fulcrum to where I place my 1 kilogram mass. So this isn't the centimeter mark, but it's how far away from the 40. So the real answer is I start at the 40 and I go 55 centimeters more to the right. So the actual answer is the 95 centimeter mark. That's where I should place this. So you have to be very, very careful. It's tempting to want to answer 55. But in actuality, we defined x to be the distance from 40 to where it is. So if I get 3 as my answer, that it's from 40, I add 3 to it, it's at the 43 centimeter mark. Here I got 55, so it's 55 more than 40, which is 95. And this is the difference between the way I defined x this time and how I could have defined it in a different way. Let's say I defined x, instead of doing it this way, I defined it like this. Here's this, 43 is at 20, here's my 0.5 at 50, and here's my 1 kilogram guy, and I called this the x centimeter mark. So I'm redoing the problem. Only this time x means where on the meter stick. Well, we do the same thing. Sum of the torques is equal to 0. I have 20 times 3 times 9.8 positive minus 10 times 0.5 times 9.8, and then I have the x. What's the distance? Remember, the distance is from the point of rotation to the force itself. Well, I'm calling the point on the meter stick x, so pretend like it's 80, the 80 centimeter mark. But what distance goes in my torque? It's from 40 to this point. So if this were 70, then it'd be 70 minus 40 would give me 30 centimeters. So I'd write 30 centimeters away as my distance. But here, I don't know 70, it's x. What the heck is x? I don't know. But the distance is whatever x is minus 40. If x were 90, then it's 90 minus 40, which is 50 centimeters. If x were 60, it'd be 60 minus 40, which is 20 centimeters. X is x, so it's x minus 40. That's the distance times 1 times 9.8. Okay, again, 9.8's cancel, and I get 60 minus 5 minus, now we got to work this out a little bit, x plus 40 equals 0. So bring x to the other side, x equals 60 minus 5 plus 40. 60 plus 40 is 100, minus 5 is 95. Well, look, 95 is exactly what the answer was. And that's the good thing about using this definition. This definition is a little harder because you have this stupid little x minus 40 thing. And thus, when you go do the algebra, you have an extra term. But the good news is, if you do it correctly, when you get your answer, that's the answer. That's where on the meter stick, the 95 centimeter mark. If I do it this way, well, I only have an x sitting there, so it's easy to solve for x. But I just have to remember the answer is not x. X just gives me how far away from the fulcrum. So I have to add in the fulcrum distance too. So you have your choice. You could do either way. You could either do it like I did the first time. X is the distance from the fulcrum. So in the torque equation, you just put x there. Solve for x, then add the fulcrum distance to it to get your final answer. Or x is the point on the meter stick. That makes this part of the equation a little more complicated because you don't want x, you want the distance from the fulcrum, which is x minus the fulcrum. And then when you get x, you have your answer. You don't have to do any more work. So just choose whichever one seems more natural for you, and you'll be fine. I can do either way. All right, I want to do one more style of problem, which is a little different, but I think we can handle it. And it goes like this. Let's say we have a bridge. The bridge has a length of 100 meters. And it's got a mass of 1,000 kilograms. The bridge is supported by two pillars, one at either end. Call it pillar A and pillar B. And what do I know? There's one person standing at the, let's say, 10-meter mark, who's got a mass of 100 kilograms. And there's a car driving along whose mass is 500 kilograms. And that car is over at the 70-meter mark. Okay? The question is, how much weight is supported by each pillar? All right. Well, let me first say each pillar will support a different weight. So you can't just take the total weight of the whole system, 1,000 plus 500 plus 100, multiply by 9.8 to get the total weight of the system, and then just say A does half and B does half. That would be nice in terms of an easy calculation, but we know the way torques work is where the weights are placed matters just as much as how much weight there is. So the fact that the 100 is located really close to A, but very far away from B, makes a difference to what A and B feel. So, how are we going to go about solving this style of problem? What we want to do is sum of the torques is equal to 0. That's what we've been doing. If my bridge doesn't collapse, if it's not rotating, then it must be that the total torque is equal to 0. But let's say I did that. There's going to be two unknowns. A is unknown and B is unknown. But I only have one equation. And I know mathematically I cannot solve one equation with two unknowns. So let me show you how I would solve this. The way I solve is I say, let's take this drawing, let's get rid of pillar B, pretend he's not there. What would happen? Well, obviously, the right side of my bridge wants to collapse. So I'm going to hold up my bridge on the right side, applying some force called force B, holding it up, making sure it doesn't collapse. And then if I could figure out how much force is required to do this, then that must be how much force pillar B supported. So that's what I'm going to do. Take the first calculation. I need to know what are all the torques. So for pillar B, sum of the torques is equal to 0. What do we have? What's the point of rotation? A is the support, so that's the point of rotation. The first thing I see is this 100. So I've got 100 times 9.8 times the distance from pillar A to where that person is, which is 10 meters away. From 0 to 10 is 10. Does that person make my bridge want to go clockwise or counterclockwise? He makes my bridge want to collapse clockwise, so he's negative. Next, we have the 500, the car. So we have 500 times 9.8 times the distance from pillar A to the car is 70 meters. Is he positive or negative? He's also negative. Next, don't forget about the weight of the bridge. That mass is sitting here, so we have to put him in. 1,000 is sitting there, and where is he? He's halfway. If the bridge is 100 meters, then the weight is at the 50-meter mark. So we have 1,000 times 9.8 times from A to 50 is 50, also negative. And then finally we have the force at B, which is called FB. That's the force. What's the distance? Well, from A to B is the full length of the bridge, which is 100 meters. And FB pushes up on a bridge, making it go counterclockwise, so he's positive. There are all my torques, and I set it equal to 0. And now I can solve for FB. Can I cancel anything? No, I can't. Notice there's a 9.8 on the first 3 terms, but there's no 9.8 on the FB term. So unfortunately, I have to keep the 9.8s everywhere. So let's have FB, so 100 times FB is on one side and everything else goes on the other. And what do I have? I've got 10 times 100 times 9.8 is 9,800. And then I've got 500 times 9.8 times 70, which is 343,000. And then I've got 1,000 times 9.8 times 50 is plus 490,000. So solve this for FB, and I get 8,428. So how much weight does pillar B support? 8,400. Fine, good. That's done. Now what? Now I want to find pillar A. So I replace the pillar back at B. So B is back in place. And now I do the same thing to A. Get rid of A. Replace A with a force holding up my bridge. Call it FA. And now FB, or pillar B, is our point of rotation. And we do everything all over again. Sum of the torques is equal to 0. What are they? All right, going from left to right, we see FA is sitting there. So the force is FA times the distance from A all the way to pillar B is 100 meters. Does FA make my bridge want to go clockwise or counterclockwise? He wants it to go clockwise, so he's negative. Next, we have the 100. So 100 times 9.8 times the distance from the 10 all the way to the 100, which is 90. Pulling down on there makes this want to go counterclockwise, so he's positive. Then we got the 1,000 times the 9.8 times from 50 to B is 50. He's also positive. And then we got the 500 times the 9.8. The distance from 70 over to 100 is 30. And those are our torques. Set it equal to 0. So notice it's a very similar process. Some of the numbers are different because for the first part, all the distances were with respect to the left pillar. But for part B, the second part, all the distances are with respect to the right pillar. So they're going to be different numbers. What do we want to do? Well, we want to solve for FA again. So FA times 100 equals, what do we have? We have 100 times 9.8 times 90, which gives us 88,200. Then we have 1,000 times 500 times 9.8. 490,000, and then 500 times 30 times 9.8. 147,000. So we get FA is 7252. All right. And what does this show? This shows that pillar A actually supports less weight than pillar B. Why? Well, notice that the heavier thing, the car, is closer to B than it is to A. So it's not impacting A as much as it is B. It also shows, of course, that you can't just take the total weight and divide it in half and say A does half and B does half. You have to do the calculations. The calculations show, of course, how much is done. So this is kind of an interesting problem. We're still doing balancing. Some of the torques is equal to 0, but you need to see how to do it one time before you can do it yourself, at least in my opinion. If you try to do it all in one equation, you're going to have two unknowns. So, with that, you've now seen kind of all the different types of problems you can see. This is a bridge problem with multiple supports. You break it up into two different pieces. Get rid of one support, replace it with a force. Do the calculation, you now have the force. Then replace the support and get rid of the other support and do the same thing. So you do it some of the torques twice. Here, seesaw style of problem. We've now seen when a seesaw is supported at the center or when it's off center. We've also seen if you know how much mass but you don't know where it is, or if we know where it is but we don't know how much mass, how to do those two styles. And finally, you have the pole with a sign hanging from it, tethered to a wall, how much tension is in the rope, and so forth. Notice they're all at the end of the day, sum of the torques is equal to 0. It's called statics, rotational equilibrium. If you're supposed to be still and not rotating, then all the torques must cancel out. So I hope this is helpful, and hopefully you continue to practice as much of these problems as you can. You'll find some on Canvas, of course. And if you have any questions, of course, let me know. Until next time.